Assalamualaikum and a very good day. My name is Nur Atira Tasha and my metric number is 24006065/1. My team and I are the consulting and development team from Lumina Bioimplants, a biomedical company focused on designing advanced orthopedic implant solutions through intelligent material strategies. Our team was engaged by a medical device manufacturer to propose a next generation total hip prosthesis. I will begin by briefly introducing our team, followed by the clinical need and the material strategy that forms the foundation of our design. This project was developed by the multidisciplinary team at Lumina Bioimplants, comprising a project coordinator, which is me, a lead designer, material scientist, and characterization specialist. Each member contributes to the design, material selection, and performance evaluation of the proposed hip prosthesis. Total hip arthroplasty is a widely performed surgical procedure aimed at replacing a damaged or degenerated hip joint. The primary goal of this procedure is to restore mobility and eliminate chronic pain, thereby improving a patient's quality of life. Clinically, total hip replacement is most commonly indicated for osteoarthritis, but it is also used in cases of rheumatoid arthritis, femoral neck fractures due to trauma, and avascular necrosis. From an engineering perspective, the hip joint is subjected to extremely high mechanical demands, experiencing loads of up to 10 times body weight during daily activities such as walking and stair climbing. Therefore, the key design goals of our implant include excellent biocompatibility, high load-bearing capacity, and long-term durability. With a targeted lifespan of more Lumina Bioimplants, our proposed hip prosthesis adopts an advanced multi-material strategy where each component is engineered to perform a specific biological and mechanical role. The structural backbone of the implant is formed using a titanium alloy, titanium 6 alpha 4V, which offers a high strength to weight ratio while promoting bone integration and reducing the risk of implant loosening. An optimized ultra-high molecular weight polyethylene liner is incorporated as the bearing system to provide ultra-low friction articulation and minimize wear debris generation. In addition, a precision ceramic femoral head made from alumina or zirconia is selected due to its extremely smooth and hard surface, which enhance long-term wear performance. By strategically integrating these materials, our design aims to address key long-term challenges in hips implants, particularly stress shielding and wear-induced aseptic loosening. This material strategy forms the foundation of our next generation hip prosthesis, which will be further explained in the following design section. I will now hand over to my teammates who will present the detailed design description and material
Hello
selection.
and Assalamualaikum. My name is Nurina Bila binti Zamridin. My matrix number is 23002657. And for my part, I will be presenting about the implant design and the components of our hip prosthesis. So our company focuses on three main goals when designing our hip implant. So the first one is strength, which is the ability of the material to withstand loading. It is important for our implant to have high strength, as patients will have to use these implants during their walking, standing, running, doing their daily activities. The next one is biocompatibility, or just compatibility, which is just how our material interacts with our biological system to ensure there are no adverse effects between tissues and bones. And it is also can also be described as compatibility between the materials of our implant itself. Lastly is wear resistance, which is basically how much friction our material is able to withstand before breaking down. So it is important for us to ensure our material has a very high wear resistance so it can stay into a patient's body longer. So this is the design drawing of our company's hip implant. As you can see, there are four main parts, which are acetabular cup, femoral stem, liner, and femoral head. So we will start with the acetabular cup, which in our design we have little pores on top to encourage bone growth into the holes. This will ensure a secure connection between the hip socket and the head of the cup. Next, we also have a smooth inner lining to prevent any friction or breakdown. And we also have extended lips on the bottom to secure the liner that will go inside the cup. Next, we have the liner that will be inserted inside the acetabular cup. It is made from smooth material to reduce friction, and we also gave a thicker layer at the top of the liner to absorb more load. Next, we have the femoral stem. In our design, we adjust it so that the shape is slightly curved to fit and accommodate the original shape of the residual femoral bone. Moreover, we also have little pores along the femoral stem to encourage bone growth and ensure a better connection between the bone and the implant. Lastly, we have the femoral head, which will be inserted into the liner part of our hip implant. It is a circular head with rounded edges near the lips, similar to the acetabular cup, so it ensures connection between the socket of the femoral head and the proximal part of our femoral stem.
My name is Noorina Patricia binti Fairozi. My metric number is 2400631/1. I will discuss the material selection and fabrication methods for our hip implant. The femoral stem is made from titanium alloy due to its high strength, corrosion resistant, and elastic modulus similar to bone, which helps reduce stress shielding. The femoral head is made from ceramic material such as alumina or zirconia because it provides a very smooth surface and excellent wear resistance. The acetabular cup is also made from titanium alloy, often with a porous surface to promote bone ingrowth. The linear is made from UHM WPE, which has low friction and high wear resistance. Fabrication methods include forging and CNC machining for metals, sintering for ceramics, and compression molding for polymers.
Hi, I'm Farzana Azian binti Faisal, metric number 24040065, and I will be talking about degradation of materials in the body. For titanium components, when the implant is placed inside the body, titanium reacts with oxygen in the body fluids to form a thin titanium oxide layer. This oxide layer protects the implant from corrosion and prevents harmful metal ions from being released. It also helps bone cells attach to the implant surface, which improves long-term stability through osseointegration. For ceramic components, they are highly chemically inert. This means they do not react with body fluids and do not corrode. Because of this, ceramics release very few ions into the surrounding tissue and show excellent biocompatibility with minimal biological reaction. For the UHMWPE liner, it is subjected to repeated mechanical movement during daily activities such as walking, running, or jumping. Over time, this causes wear and produces very small microscopic particles. These UHMWPE wear particles can trigger an inflammatory response in the body. Long-term inflammation can lead to osteolysis, which is the loss of bone around the implant. As a result, the implant may become loose and eventually fail, requiring revision surgery.
My name is Novatricia Izandra with the metric number of 2300126/8/2. Material characterization studies material properties to ensure hip implant materials are safe and perform well inside the human body. There are three main types of material characterization: mechanical testing, imaging, and chemical and surface characterization. Mechanical testing checks material strength and durability. Imaging examines surface damage, and chemical characterization ensures the material is safe and corrosion resistant in the body. Hip implants must withstand repeated loads in the body. Mechanical testing using the Instron machine checks if the material can support daily activities, while SEM imaging identifies wear and cracks that may cause implant failure. Scanning electron microscopy or SEM is a high-resolution imaging technique using a focused electron beam producing much clearer and much detailed images. SEM helps engineers analyze surface morphology, wear patterns, cracks, and defects. This helps evaluate surface damage and predict long-term implant safety and durability. The Instron machine is a mechanical testing system used to apply controlled forces to materials. It measures properties such as strength, stiffness, and deformation through tensile, compression, and fatigue tests. These tests simulate real-life loading conditions experienced by hip implants inside the human body. The instrument machine ensures implant materials can withstand repeated loads, supporting safety and quality standards.
Hello doctor, so my name is Nurafika Zati. My matrix number 23001133/2, and I will be presenting the slide, which is the chemical and surface characterization. So, why is chemical and surface characterization is super important? It's because it will be inside the human body for many years. Body fluid can cause chemical reaction and degradation. Surface properties can affect the biocompatibility and implant fixation. It will ensure the long-term material stability, reduce wear and failure, and it also improve implant lifespan. So the first one we have the FTIR. So this slide I will explain the use of Fourier transform infrared spectroscopy on the UHMWPE liner. So FTIR works by passing infrared radiation through a sample to identify its molecular composition based on absorbed wavelength. And in this study, FTIR was used to analyze the chemical stability of the material, which is the UHMWPE, and it helps identify functional group and detect sign of oxidation, chemical aging, or material degradation. And this is super important to ensure the liner does not chemically break down when used inside the body. So overall, FTIR analysis helps confirm the material safety and durability and resistance to excessive wear and particle release. So the next one we have the GPC, and in this slide I will show you the use of gel permeation chromatography on the UHMWPE liner. So GPC is used to measure the molecular weight distribution of polymer by separating the polymer chains based on their size. And for UHMWPE, GPC helps to evaluate polymer chain degradation. A decrease in molecular weight indicates polymer breakdown, which can lead to reduced mechanical performance. And this analysis is super important for predicting the long-term wear resistance of the liner and reducing the risk of implant loosening. Overall, GPC will ensure that the material, which is the UHMWPE, maintains its strength and durability for long-term use. So the next one is the contact angle. Contact angle is the angle formed between a liquid droplet and a solid surface, and it shows how well the liquid spread on the material. So when the contact angle is small, the surface is hydrophilic and it shows that it has a good wettability. When the angle is large, the surface is hydrophobic and the liquid does not spread well. And contact angle measurement is super important for biomedical materials such as titanium femoral stem and ceramic femoral head. Surface wettability will affect the protein absorption, cell attachment, and biocompatibility. And in general, a lower contact angle is preferred because it improves interaction between the implant and the body tissue.